So once again, this is something that's been put together by the National Hydrologic Warning Council. The talk today is going to be about basic hydrology with a particular emphasis on how that pertains to flood warning professionals. My name is Jeff East. I work with the United States Geological Survey, and I'm located in Houston, Texas. Just to give you a little idea of sort of how we're going to be spending the next 45 minutes or so. Going to do just a little introduction to the National Hydrologic Warning Council for those of you that are a little bit new to this group. Talk a little bit about the actual work group that has put together this presentation as well as some future ones, and just give you an idea of sort of what's to come. Then we'll talk about the basic hydrology for flood warning professionals. It's again a few different concepts that we'll discuss, all in relation to flood warning. And then we'll have a wrap up. Would like to encourage people to use the chat function in the Teams Live. You can go ahead and type in any questions or concerns. And there's moderators that will attempt to either answer those questions if they can. If not, either we'll save them for the end, or if it's something that's particularly sort of pertinent to where we're at, you may even stop at that point and address it then. So please use the chat function right now. Everyone else is muted, so we won't be able to hear you otherwise. So once again, just a brief introduction for those of you that aren't very familiar with the National Hydrologic Warning Council. It is a nonprofit organization. You can certainly read the vision statements and the mission that's on the screen right now. I think the fourth bullet is the one, hopefully, that sort of the kind of ties it all together. One of the unique features of this group is that it's a membership-driven organization, governed by a group of volunteers that form the board of directors, and so by organizing in this fashion, it helps to keep a lot of the work that's done sort of more relevant. The things that really affect individuals in this arena, sort of on a day-to-day basis, and things that are challenging. This group is able to sort of tackle them at that level because once again, it's a group that's sort of run by the members. Benefits, like any professional organization, certainly there are networking opportunities and other things. And once again, you kind of read these bullets. Some at the bottom of the list, I think is another thing that's maybe not necessarily unique, but certainly rare for some entities that you might join. A lot of support. Again, it's a group of individuals that are in the field doing a lot of the work. Certainly a number of the members are, and so very hands-on and understand the challenges that others face, and so a lot of interaction, trying to help out at all levels through the different organizations, and also things that come up that maybe are fairly important, overall. It allows a collective position to be taken and brought up, from this organization that maybe you or just your wherever you work doesn't have quite the same voice as if it comes up from a national organization. A little bit of information about membership for those of you that aren't members. Currently, these webinars are open to all. However, we do want to encourage people to join. Once again, there's a lot of benefits, certainly beyond. This is just one aspect of what the group is trying to do. If you are interested, certainly you can type something in the chat right now and someone can give you some information, or go to the web page and I'll provide a link later and you can get that information. The group, as I mentioned, that sort of is in charge of what we're doing today and will be doing into the future. It's a training and professional development committee. It's a relatively new group that's been put together, to try to address some specific concerns. Once again, there's a lot of people doing a lot of things. However, there's some consistency in the challenges, and some of the information needs. And so in order to try to fill that and provide some resources, this group has been put together. Josh Herbert is the chairman. He's in Calcasieu Parish, Louisiana. You can kind of read the other names. And, hopefully you can also see by the affiliations that this group is made up of, individuals in the private sector, vendors that provide the equipment and other resources to kind of do the work, as well as some in a governmental role. So a good cross section of people that are in this work. And so hopefully this group is able to sort of bring to bear a lot of information. Another mission statement and objective for this group, and as I mentioned, the idea is as individuals come across things that where they would like to get some extra help or knowledge, this group tries to identify that, bring the education, identify resources or individuals that maybe can bring that to the whole. Sometimes there's things such as standards and other things that really would benefit everyone in the community. And so this group is investigating that. And, sort of the last bullet is, sometimes, there's questions about certification programs, to ensure that individuals in this arena, have all the knowledge and are up to a certain level of education and knowledge base. So, looking into those kinds of things. So that's what this group is doing, and we certainly encourage people to interact with us once again, both during this as well as external offline from this meeting, and we'll provide some information for that. So today, again, talking a bit just about basic hydrology, but with the slant of trying to make it more relevant to flood warning professionals. And so hydrology in of itself is a very broad, scientific endeavor, a lot of different sub areas, that can take a lot of time and effort to dig into. And today is just sort of an overview of certainly some of the more relevant pieces of the puzzle, that we have to deal with in the flood and other emergency management responses. So, we're going to start off just talking about some basic concepts, jump into the hydrologic cycle, things that we've seen in the past, talk about some of the components that may or may not be, particularly relevant, some other things that are going to affect, once we get rain or some sort of precipitation, if it all just went into a channel and went downstream and sort of behaved itself, that's sort of the ideal. But when it starts to interact on the landscape and in throughout watersheds, there's some things that we need to try to at least have some understanding so that we can put things in context. And then last, once that water gets into some sort of a defined drainage system, then we sort of change over to thinking about stream flow or discharge, or there's some other terms that are used. So trying to sort of look at, those components that affect what we're doing. So, sort of basically, what is hydrology? Fundamentally, it's the study of water. So, very simple, yet once again, very, very broad. It can mean a lot of different things to a lot of people. So to, sort of tighten that scope, I came up with more thinking about an applied hydrology definition, which in a way is the study of the occurrence of the water, how much is there, where is it, movement, does it move through the hydrologic cycle, where does it show up, where does it not show up, at least in terms of floods and things, and then the distribution. So the dynamics of, where is the water, how did it get there? How quickly did it get there? And what does it need to do to kind of move through the system? So that's sort of where we're at. But, is with most earth sciences, there's a lot of overlap. There's a lot of area that, sort of bumps up and actually shares with some other scientific topics. Things such as meteorology certainly, is a whole nother concept that affects hydrology and vice versa. Soil sciences, hydraulics, watershed delineations. So there's a lot of other things that all come to bear when we're looking at floods and managing floods and understanding floods. And so this is just sort of one small piece of that puzzle. But certainly understanding that it's important, but that there are other things. And so for today, we're just going to sort of keep the focus on the hydrology side of things. So the hydrologic cycle, probably, this is something that most people will become, familiar with and are introduced maybe throughout some of their grade school or middle school experiences, depending on, if you go to college in certain sciences degrees and things, you're going to get more exposure. But once again, this is something that I think, most people, can sort of see and understand. The sun rises over the ocean and, starts to heat the water. Over time, there gets to be the right conditions, and so you start to get evaporation. That water, the moisture kind of moves up into the atmosphere. The clouds get moved inland over the land. Maybe start to climb over some mountains. You start to change pressure and temperature. And it gets to the point where, all of a sudden you start getting some sort of precipitation. Once that, falls on the landscape, where does it go? Some of it's going to seep into the ground, and where it goes there, that once again, that's an entire discipline of learning, that we'll sort of gloss over. Some of it's just going to sit in puddles and things and be stored. Other is going to run off and eventually find its way into a draining system, whether it's just the natural drainage or some sort of man-made and improved drainage. So fundamentally, I think most of these general concepts are pretty easy for people to see and have a grasp of. But this is where we sort of have to dig in a little bit and spend a little bit of time on some of these and understanding or monitoring and predicting some of these components. Certainly in flooding, the precipitation is what drives it. Certainly there are floods, maybe from snow melt and other things that don't happen immediately after precipitation events. However, the vast majority of what we think of and what we have to deal with, are tied hand in hand. So you don't get much rain, maybe you don't have that many floods to deal with, but when they do show up, based on other characteristics, they may be more severe, less severe, etc. So if we can monitor and put out equipment to record information, so that we can start to quantify these things, the goal there is to then, improve our understanding, so that we can, better manage different events. And when things are going well, we have enough information, and sometimes when we don't have enough, but the need is there, we'll try to do forecasting. And so, what may start out is if the news comes on and says it's going to rain a couple inches tomorrow. Well, in our mind, we know, okay, for where I'm living, maybe that's a lot of rain, maybe that's very common, but we may have some sort of general qualitative assessment of what probably is going to happen. The more we sort of dig into it, then we start to think of other factors. Has it rained recently, and so is the ground saturated or not? Do I live in an area where 2 inches of rain in a day is not a big deal, or do I live in an area where that's half of my annual total? So those things start to come into our mind to come up with a qualitative picture of probably what we believe is going to happen. And going further into it, when we start to get into the flood warning and emergency management, so that's where we want to actually monitor these conditions, to get more quantitative answers. And that's really the end game. Is if we knew where the rain was going to fall, how much, the exact time, as well as, you know, how it's going to react with its environment, and ultimately, you know, where the flooding is, exactly how bad, exactly when. You know, that's sort of the end goal. The more advanced notice we can come up with is the goal. So these other factors, once again, snow melt, evaporation, and filtration. Infiltration, when we're talking about flooding, is sort of the one that still, you know, is important to understand. And we'll get into some of the details of that. But, you know, while it's not probably, it's definitely not the driver, it certainly has an impact on, you know, kind of the conversion of the precipitation through the process and to what ends up becoming runoff, and then eventually into, you know, the drainage network as stream flow. So some knowledge of what infiltration is happening and the differences in it, you know, comes into play. The others, you know, not quite as much, although snowmelt, once again, we'll talk a little bit more about that. But while it's not usually a single event where it snows and then we get a flood immediately, certainly there's a lot of areas where, you know, a large amount of the flood issues, or at least the high flow issues, you know, are derived from snowmelt, and we'll touch on that in a bit. Some terms, you know, because like a lot of different sciences and areas, you know, different words and different phrases kind of eventually start to mean subtly different things based on their application. And so just at least for the purposes of the discussion today, I thought it was worth bringing up a few that once again, in your particular use might be subtly different. You know, a watershed, really a watershed, or sometimes people refer to basins or even a sub-basin. At the end of the day, fundamentally, they're all sort of describing the same thing, which is you've got some sort of a topographic boundary on the land surface that would define an area that if rain was to fall just inside of that boundary, anywhere inside of that boundary, you know, that the water that actually stays on the surface and makes its way through the drainage system, it would eventually get to a single point. It would drain all to that same end of the funnel. And anything just outside, you know, is going to go some other way. You know, we don't know necessarily where, but we do know that it's not going to follow that same path. And, you know, like I said, depending on the context and the work, you know, in some areas, the difference between a basin and a sub-basin is very important. But just in the general hydrologic sense, if someone does just say they're talking about a watershed or a basin or a sub-basin, and you know, we're just talking about hydrology, they're all kind of describing the same thing. It's more an application is usually where those definitions sort of are subtly different. Precipitation, again, for someone that lives in the South, such as myself, you know, when I think of precipitation right away, I automatically think rainfall, you know, every single time. But, you know, it really means, you know, sort of any atmospheric deposition, whether it's rain or sleet or snow. And for those of us, you know, certainly many of us in the South and definitely in Texas, you know, last week was a good reminder of that, where we saw sleet and snow. And so, you know, where you're at and which form of this, you know, is sort of, you know, what you have to deal with, or at different times of the year, what you have to deal with. Those are things to consider, you know, once again, in terms of how you monitor for them. What kind of time frame do they react with the environment, and ultimately, you know, maybe become an issue that you have to deal with. Runoff, again, at least for the purposes of today, what I'm calling runoff is you know, the water cycle that I described. You're going to have some sort of precipitation, and maybe, you know, we think rainfall a lot of times. So it hits the ground. We said before, some of it sort of, you know, maybe seeps into the ground and does other things, but eventually some of it is going to actually start moving across the land surface until it starts to collect in some sort of a drainage. You know, whether that's out in the forest and it just starts to find little swales or other things, or in an urban setting where it comes off of people's houses through their gutters, eventually in a storm gutter, and starts to collect. And, you know, in any setting, you know, some of it's going to start to move down and get into some sort of a drainage system, whether it's natural or man-made, and then start to flow downstream until it does sort of get to that point, where it's leaving a given watershed, however it's been defined. And so the runoff is sort of that amount of precipitation that isn't lost to something else. It's the volume of water that eventually starts moving through the system that for flood, that's what we have to deal with. Stream flow, or once again, maybe, sometimes people use the term discharge, or flow rate is another one. That's once it gets into the defined drainage system. And, we're seeing the water moving down a creek or a stream or a river, bayou down here. And that's going to be a definition of, it's actually a volume of water that's moving past a given location in a given period of time. And so, we want to deal with volumes because once again, that sort of dictates how much a stream channel can hold, how much a entire river basin gets, how much volume falls in it, turns into runoff. Eventually it has to move its way through the system. And so, knowing sort of key features about that, and certainly the monitoring of some component of the runoff, knowing how high the water gets, is valuable because that tells when it starts to get to the point where it's coming out of a stream bank and so forth. So these are just some terms to kind of keep in mind. And like I said, different areas might have more subtly precise definitions that you use, but for the purpose of the day, moving on to precipitation, as I said, that's by and large, this is the driver of floods, and even in snowmelt, it's coming from precipitation. It just may not be an instantaneous phenomenon where it snows today and you're getting rainfall in a few hours, but still the precipitation is where the water, the moisture is getting onto the watershed. Concept of collecting the information is pretty simple. We just collect, an amount. In some settings and for some purposes, having a group that has some sort of a collector and they put it out at their house or wherever at their office, and every day they check it, that sort of information has value. Once again, you at least a certain amount over that day period, and that can help define some things. But in the flood warning business, usually that's not quite at the level of detail we're after. We need something that can be used to sort of predict what's happening in a much shorter time frame, and the details matter, and that's sort of the goal here. I'm not going to get in. I just wanted to list a few things here, in terms of the instruments and what kind you select and where they go and everything is important. But this is really meant as sort of a kind of a teaser. Because next month in March, we're actually going to have the next seminar will be about precipitation and data collection. And so we'll get much more in depth about some of the subtleties there and what to worry about. And certainly I'm sure there's many on this call that are already well aware of those details. But just to know that the type of information that you need is important. For floods, usually a total precipitation for an event, maybe that helps after the flood to do some sort of verification of things, modeling, other aspects. But during an event, when we're trying to know exactly what's happening, once again, our ability to simply sort of hear, okay, we're going to get a little bit more than I'm used to hearing, so it may flood. That's of some use to sort of get your attention. But if we want to use the information, we need something more precise. Most of the time we need something, that's going to give us an intensity. And so once again, if we were to go out and collect, data and we know that it was 2 inches in a day, that probably means something in most places. But if, 2 inches an hour, that means a lot everywhere. That's a very intense rainfall, and systems, generally aren't designed necessarily to, be able to carry that kind of flow that rapidly. And so, that's something to be aware of in designing systems, as well as, understanding how they affect, certainly spatial variability and how rainfall, occurs over the land, over the Earth's surface is another, entire topic that could be discussed. A lot of variability in how and where the rain, occurs, and that affects, once again, sort of all the way down to the point where it runs off. But End goal is, we're probably going to need rainfall intensity, and the details matter so that we know that if we're collecting it to certain standards, a certain way, that we know that a 2-inch rain event that falls a certain way, we have more confidence in what's going to happen as a result of that, as opposed to if the way that we collect the information and the way that we categorize it is a little bit more general. What's normal for your area? That's, like I said, that's probably just going to be something that you're going to learn once you live somewhere. And if you move somewhere, new, you sort of have to readjust, your own sort of gauge. Generally, if we look at this map, we kind of tell those areas of green. I know the scale's very difficult to read, but the green areas, a little bit more, annual rainfall amounts. You get down in the Houston area where I'm at, annual rainfall 40 inches, in that area is, sort of what we expect. You kind of start to move over to the, arid Southwest. Certainly that's, those numbers drop way off to the point where you're getting very little rain. You move up to the Northwest, you get significantly more rain. So, knowing a little bit about what's common is going to be important. Not just so you know whether it's something to respond to or not, but there's other things. If you live in an area where very intense rainfall events are common, then probably the drainage system is going to reflect that. Certainly if it's an improved drainage system, things are going to be designed for that. Whereas if you live in an area where the rains are usually more, a big front comes across the Midwest, you can sort of see it coming, a day away. You know about what the volume is going to be, and it's probably not going to be that intense. Then that's sort of a different reaction, a different response. Knowing what the type is, like I mentioned before, up until last week, all I'm thinking is rain, but snow and how much is falling. If you're in the mountains, you're keeping track of the snowpack. And this time of the year, you're trying to see how much there is. And certainly there's water supply concerns, and that's a big issue to know there's enough snowpack, to support that. But also, how much is falling, how quickly it warms up when we get into the spring. Do you get a big storm event, where we actually get precipitation on top of that? That's a whole different hydrology than maybe coastal plains or something along the eastern seaboard. That provides its own challenges. And so, local knowledge is just critical to kind of know and judge, that. And once again, those annual amounts, same thing. And really the intensity is just, a big driving force, that we really need to, keep in mind because, 2 inches is not, always the same depending on how it falls. Just sort of a completeness of discussion, evaporation and transpiration. Conceptually, I think, most people sort of have an idea. It rains, or even if it doesn't rain, you've got a reservoir, and if it starts to get in the summer, it starts to get hot and so forth, and maybe some wind, you start to lose some of the water that's ponded on the surface to evaporation. It starts to convert, and move up into the atmosphere. Same thing with transpiration. It's the water that gets pulled into the plants, eventually into the leaves, and then, same sort of phenomena happens where that moisture moves up into the atmosphere. How fast that happens and when and the amount, these different factors that are listed sort of control that. But, sort of the key for this talk is, the time frame there is much longer than what we're usually talking about. Certainly in rain-driven events, where we're talking about, many times we're talking about, a day, maybe a couple days at most. A lot of times the real serious, effects are in the order of hours. So, not a really big component, but, in terms of water budgets and other things, it's something that needs to be concerned, in that context. But for our purposes for flooding, usually evaporation and transpiration is something. So that's sort of a gimme that we get to, sort of put to the side and not necessarily for flood work, have to consider. As I mentioned previously, infiltration, and once precipitation in whatever form gets on the land surface, where does it go? Infiltration, the water seeps into the ground, enters either a shallow water zone or, eventually maybe into a deeper groundwater aquifer system or what have you. Entire branch of science that deals with that. But for our purposes, how much water gets into, that system and sort of how quickly does it get in? So the timing and the magnitude again is sort of the common thread here, because that tells us ultimately how much volume is left that's going to get into the drainage system where we need to, pay attention. So that amount and that rate, very important during events. It is variable, both spatially as well as temporally, based on these different things that are mentioned. Given all other things being equal on, let's say, a plot of, just sort of undisturbed land, maybe some loam, a little bit of sand, a little bit of clay, or what have you. If you get a 2-inch rainfall over a day and it's kind of just a nice soaking, that's going to soak in and infiltrate, sort of one characteristic way at a certain rate, and we'll get to a certain volume maybe where it can't hold it. But if all that rain comes in a short period of time, you're going to have more volume to deal with just because the system is not able to absorb it that fast, probably. So, the soil characteristics too, they can change widely in somewhat small areas. That's a relative term, but soil moisture is another one. If it hasn't rained in several weeks, maybe the ground is sitting there just waiting to pull up some of that initial precipitation. Other times, if it has been a soaking rain for a few days prior, and now you're going to get that heavy one on top of it, you can expect a different response. Land cover is a huge one. I can't say most of the time, but many times the reason we're worried about floods and we're in the flood warning business is because it's an area certainly where humans live and have developed. What comes with, individuals moving in usually is some sort of urbanization, improvement of the land with concrete and other things that will change, the watershed properties. And so those areas where worrying about the flooding because it's going to affect, people and humans and property is also the area where, we're making these changes. And then another one, certainly is the slope. You could imagine water that's falling in a coastal plain or somewhere where it's, very flat. That water is going to seep. Whatever runs off is going to move across the land at some given rate. Whereas if you're on a mountainside, that's a completely different hydrologic setting where you're going to get a much different response, much more rapid response. Even if other factors are the same, the rainfall amount stuff. So each of these is important to consider, in where you live. So as I mentioned before, runoff and at least for today, it's calling it sort of direct surface runoff. It's that amount of whatever precipitation, that falls on the Earth's surface that's not lost to the infiltration that we just talked about, or maybe some other surface storage. You have puddles that sort of gather, in areas that are sort of isolated from the drainage, and the water just sort of sits there indefinitely. So some water is sort of removed for that. Other abstractions that, some of them timely, like evaporation and things, are going to happen over time. But what we're talking about in this case is, mostly what's going to be infiltrated into the ground and maybe lost a little bit to surface storage. And so sometimes that's just called the excess rainfall. Same characteristics that I just mentioned before, in terms of infiltration are a lot of what drives this. The infiltration rate, as you see this graph on the upper right. So the precipitation are the red bars. This HIETA graph is the time series. So across the bottom, as we go across time, on the left, we're looking at, amount of rainfall. And I just left units off just because some people are used to metric and I only deal in English. But so let's say we got, 5, 6 tenths of, an inch of rain is a maximum. And, the storm comes, it gets intense, and then it drops off. The infiltration rate, could be described by this yellow line. And once again, sort of these same units. Early in the storm, the ability of the ground might be such that it can actually absorb quite a bit of water. And so you get a little bit of rain early on, but the intensity is such that the ground has no problem with absorbing that. But, that ability starts to decrease, fairly rapidly usually, until it gets to a point where either the amount of, what it can actually take gets so low that even if the, intensity doesn't increase, or it gets more intense, and you eventually get to a point where the rainfall starts to exceed the ability of the water to actually, infiltrate the water, infiltrate into the ground. So you start to get this excess precipitation. And so where does that go? Well, then that, usually will turn into some sort of runoff. It starts to move across the land surface and get into these, drainage systems and start to move downstream in the watershed, ultimately sort of out the end of the watershed in whatever stream and whatever scale we're talking about. What's important here? Well, sort of, the timing again. Here for this sort of hypothetical storm, here's sort of when the peak of that is. Well, usually there's going to be some offset. How much is that offset in time? Is it immediate? Is it days? That can be governed by some of these factors here, that we're talking about. The land cover, the slope, the size of the watershed, and what's, some other characteristics. So this is very important. If we've got rainfall information, we put out rain gauges. If where we live, this is on the order, a lot of times for a certain storm, this is on the order of 15 minutes. That's a big deal. We're going to need to do things maybe a little bit ahead of time based on the rainfall prediction. If this is on the order of 6 or 12 hours, maybe we can afford to wait and see what the storm's doing. But sort of knowing how these all interact and generate this runoff, this is the component we're worried about. And then once again, the magnitude of how much of this runoff, is generated. So the timing and how much, and the how much is going to dictate, whether or not the natural or improved drainage system can handle it and convey that water away from, causing problems. So timing and magnitude again. Just going to show a few, some graphs, and I think these all are going to be conceptually pretty easy to understand, but at least for the purpose of demonstration, sort of the effect of that precipitation intensity. You have, a rain event that comes in, the exact same volume of rain falls in this instance, and I didn't necessarily put the effect of the infiltration, but it's sort of implied on this side on the runoff graphs. The exact same conditions, same sort of soil, same size, everything else, and so the same storm comes across. Here, you're going to get a little bit, probably a slower response and not quite as high as if the event, comes a little bit more intense, comes a little bit early. And so here we can see the difference in how the rain falls is going to cause these differences in the timing. Now we're not looking at the difference of when the magnitude of the rain is, but just, how long for the same rain amount do we have to actually before the worst case scenario is on us. So this is going to play a big part of it. This magnitude, same volume. So if they say 2 inches of rain tomorrow, well, are we going to deal with 800 cubic feet a second? Or are we dealing with, 1,500 cubic feet a second? And how does that interact with the drainage system? Is that going to be a problem for, life or property? So knowing the intensity, very important. Watershed size. So now if we back off and we say the exact same storm and other things are the same, but we're dealing with, an area where I've got 3 or 4 smaller watersheds, and by smaller, maybe let's say 50 square miles, and then you've got a large river that comes along that you have to deal with, and that one's on the order of 2,000 square miles. And once again, these are all just relative terms, but same event falls, well, the small, because you're going to have a smaller watershed, you're going to have less area, and so ultimately less volume of water that has to get through the system. So you're not going to see that sharp rise, let's say, if the precipitation event isn't real intense. It's going to kind of come along. A bigger event is going to take longer just by, usually more water has to go a little bit farther, comes through the system. You might have to deal with, larger volumes, but it's going to come later. And typically, if we're talking about larger watershed, the natural drainage system is already, developed on its own. It's going to handle these. And so, when you get a large event or an intense event on a large river, maybe the volume is more than the system can handle. But hopefully the thing that you've got going for you in many settings is you've got, relatively speaking, more time that you would than if that same event fell on a smaller watershed. It's all relative, however, and certainly, that can change drastically. Large versus small on a mountainside, probably the difference in the timing here is going to be, much less maybe than if we're talking about other settings. Land cover, a big one, and once again, urbanization is a very big one in flood warning, because it also happens to be where a lot of the life and property are, that we're trying to protect. So you get the same rainfall, but it falls on, an urban area, concrete. It's not able to infiltrate. Not only that, so you got more volume, but that abstraction, of the rainfall, there's going to be none from the very beginning of the storm. It's going to start to drain off immediately and get into some sort of drainage network right away. And so you're going to have to deal with a much quicker event. It's going to respond very rapidly, and it's going to have more volume and ultimately, have more of a peak discharge value, peak runoff value that you're going to have to get through your drainage system. And so areas that maybe were natural and then over time have been, changed and developed, very common to see, if you happen to have, information and data collected that, events that happened 30, 40, 50 years ago, maybe are these where it's a little bit more of a rollover, sort of a hydrograph, whereas now you're seeing this kind of response. These are the ones that we have to worry about and understand that, as our watersheds change, this is probably going to keep, being something to consider, unless there are other things put in place, detention ponds, other factors that are meant to offset this. And so if some of these, engineering structures can be put in place, this may be what they're dealing with in terms of the runoff, but we can put some sort of an engineering solution to cut this hydrograph, down to size, store some of the volume of water to let out over time, and maybe what's actually getting downstream where we're worrying about is something, that looks more like it was pre-development. And so that's the goal of the engineering, designing, and some other ways of dealing with it. Watershed slope, already mentioned, and I think it's easy to understand. If you get on a skateboard and it's out in your driveway and you've got a very slow incline, you're going to move down at a certain pace. If you're coming down your roof or you're coming down a mountainside, much quicker. Same thing. And so depending on where you're at, this is going to affect that timing, and that's a pretty easy one to understand. Going to just sort of touch on this a little bit. The runoff from snowmelt. Like I said, there's large areas. This map sort of shows, floods over, a long period of time at USGS gauges, and there was an attempt by University of Connecticut to sort of identify, flood events that at least had some component, due to snow melting versus those that were just rainfall only. And so, it's not just in the mountains. It's kind of all over the country, all across the north, and even there's some down in Texas, historically. And so, knowing that these happen, and if you're in an area where they happen often, a big deal. Now, usually the timing is more predictable, but their extended duration. And like I said, this time of the year, I know in colleagues of mine that work up in areas, where there's a lot of snow, they're already preparing. They know that once it starts warming up and the snowpack starts melting, the streams are going to get up, and they're probably going to be up for a month or 2 months or 3 months or, some period of time, depending on where they're at. Now, hopefully the system is such that the drainage will allow it to move through and not cause damage. But there are factors, in snow hydrology to kind of consider. And once again, the rate of the melting, and if you get it, those things, are concerning. So as I mentioned before, one the precipitation hits the ground, moves through the system, and gets into some sort of drainage system, then we're going to call that stream flow, or discharge or flow rate. There's a lot of different terms that for the purpose of today, we can sort of use interchangeably. In some settings, there are maybe some more precise or specific reasons. So I think I dropped off for a second. I apologize. Hopefully I'm still back on. Um, so, the idea is the water gets into that drainage system, and can the natural or enhanced drainage system handle that volume of water that's going to move through? If it's coming all through at a constant, that may be easy to deal with, but usually it's going to change over time. You're going to get a large slug of water, and then it will need. We do need to know that volume, because once again, that will play into how much can the channel hold? When does it exceed the channel? Usually, at least in the U.S., we measure it in cubic feet a second. Sometimes meters per second is used as well. CFS, and where I live, if you say CFS in the wrong group, people think of chicken fried steak, but that doesn't happen to be the case in this term, although sometimes I prefer chicken fried steak to cubic feet a second to deal with anyway. We measure it a variety of different ways. There's various, my agency, the U.S. Geological Survey, we have a lot of stream gauges. There's many other entities that measure stream flow and gauge flow and provide time series data. There's a couple different ways you can sort of measure a given volume of water at a given time. If you can capture it, say a pipe that fills up of a known volume at a certain time. In natural streams, we tend to go out and we'll measure, sort of as this picture depicts, where we measure the velocity across the stream in different locations, and then we get these areas and sum them all up. Also, a lot of what's done, that really pertains to what we're talking about today is just using hydraulic theory. If we know rainfall and other characteristics, we're able to then, predict what the runoff is and ultimately what that stream flow is. And so that's very important, providing whatever information we can. And if we happen to not only have the rainfall data to run those models, but we also have stream flow data at key points to help tweak those models if needed, that's another very useful part of the puzzle. If not stream flow, the stage data. If we don't have stream flow, but we actually know how high the channels are, that's another very important piece of the puzzle. So, what are some of the applications in places where you have it? Like I said, if you can use the theory, couple that with knowledge of topography, and we're getting better, more high resolution topography every day through LIDAR and other methods, channel dimensions, hydraulic theory, and you put all the pieces together, then we can start to actually use and develop management products. Flood inundation mapping, we can determine ahead of time for a given storm event that we assume will generate a certain amount of runoff and a certain amount of flow. What areas are we going to predict are going to flood? Flood forecasting, where we want to be able to say with some level of certainty what's the timing and what's the magnitude. When is this going to get there, and how bad is it going to be? Very, very important, and a key part of what we do. How does that happen? So if you happen to be in an area where a stream gauge does exist, that entity has probably put together what we call a rating curve that's going to relate gauge height, or sometimes it's referred to as stage, or just water surface elevation, sort of whatever you want to call it. How high is the water getting at that location? And then what is that flow, the discharge and stream flow? In the right situations, you can make measurements, like I'm showing here, and then develop this relation, along with other knowledge of the hydraulics of the area, and come up with the relation. And so those simulation models, where they could take the rainfall and other knowledge, come up with a discharge and say, tomorrow, we predict it's going to be at a certain discharge. if you've got this relation now, if this is a pretty predictable relation, we can say for that discharge, what do we predict? How high is the water going to get? And then we go back to our topography and look and see what kind of inundation it may or may not, generate. So having the rainfall data drives the whole process. Having stage data helps to verify. Having discharge data where you can helps to verify. But it all starts with that rainfall data, and then some knowledge of what's going on the environment in terms of land use and infiltration, and how much water is going to get to the stream. So in summary, I think I probably said timing and magnitude, I don't know if 10 times or 20 times, but that's the key. We can all, in our own minds, in our own scenarios, sort of, from our background, know certain storms are probably going to lead to certain scenarios and certain conditions, and some get our attention more than others. But if we can fine tune that, we know the actual timing and we know the exact magnitude, and convert from qualitative to quantitative, that's very good. That's what we're after, and that's what individuals in this line of work, and that's what we're doing it for, is to help support those decisions to protect life and property. When all else fails, hydrology, if the only thing you remember here is water flows downhill, just sort of remember that, and hopefully you can backtrack sort of whatever when you're out doing your work, where's the water going to go? That's sort of the basics of hydrologists. That's how I chose my career when I was going to school. It was the first thing that a professor said to me that I actually understood. So once again, there's some additional training opportunities. We're doing these monthly webinars. I mentioned before, we're going to be talking about rainfall next month. David Haynes, who's definitely an expert in in this topic, has a wealth of knowledge. So if you've got any questions or any thoughts about rainfall data collection and instrumentation, etc., definitely do not miss this one. We're going to hold these third Wednesday of each month. So kind of keep coming back and checking. Just a little shout out that as of right now, we're hoping to have a workshop in Texas in fall. Obviously, everything's a little tentative with COVID and so forth, but keep your eye on the website that I've got listed if you're interested in that and in the area. Certainly, that's something that is an opportunity to interact and network with others, and hopefully build some relationships. Once again, with that, Josh Herbert is our chairman, and so if you need to get in touch with him about anything, here's his email. Put my email on here as well. If you have anything that you'd like to either have a presentation on, or if you've got topics that you would like to discuss and even present, we'd really love to hear from you. Please type anything in the chat, and we can respond to that. And if there's questions that people need to actually ask verbally, as needed, we can probably turn off the mute and handle that right now. But so right now, I'll go ahead and open it up and see if the moderator has anything for me to follow up on.
Thanks for the great talk, Jeff. We really appreciate it. It's amazing how we can be so involved with this technology and sometimes forget the basics of water flowing downhill. So I really appreciate you taking the time and sharing your knowledge with us. I want to correct me if I'm wrong. There's a couple other members on the training committee here. I believe that we're actually scheduled for the last Wednesday of every month, not necessarily the third Wednesday of every month. But again, if someone wants to correct me, feel free to step up and do that. I did have a question for you, Jeff. Because we were talking about all of this, rainfall runoff and we talked about the relationship between rainfall and how high the water gets. You talked in depth about how important it is, the saturation of, for example, the soil or the rainfall intensity. And I was wondering, traditionally we've only been able to get this information by sensors, and the sensors haven't been great at rainfall intensity and soil moisture. Now the sensors are a lot better at soil moisture and rainfall intensity, but we've also got a lot of ways to compute that just through models. You can look at the rainfall over the last month, and you can use gauge adjusted rainfall radar to get a much better idea of intensity. So I was just wondering, in your experience, do you see this going more towards monitoring those parameters by sensors, or do you see that more as something that's going to be monitored by equipment out there?
Yeah, very good question. I would say, as you mentioned, sort of in the absence of being able to collect very precise, reliable, information from the environment, the limits of the technology we sort of reached, years ago. So in the absence of that, other methods were designed, and like you said, different models, to come up with what were, the best answers at that time were developed. And, they're fairly good. They're fairly robust, work in a lot of conditions. Occasionally you'll get some sort of an outlier where all of a sudden that model just, for unknown reasons, maybe it doesn't work. I guess, what I'm seeing is there is a little bit more interest in monitoring things like soil moisture, and certainly rainfall, and specifically collecting accurate data during high intensity rainfall events is a pretty big focus that I've noticed, both in USGS and then other places that I've visited with. And that's where some of the details, and I'll be curious, for David next month to hear about it. But, in my office, back in the 90s, we would find a rain gauge, and, sometimes I don't even know where we find it. It fell off of somebody's truck, and it was, hey, we got a tipping bucket, let's put it out there and collect data. It would provide numbers, but really there are limitations, physically, and if the different components in that really didn't work well at high intensity. So we were probably under registering and things. So, I think it's going to be a combination. I think with better knowledge about the limitations of the sensors, much better sensors, that are available, and technology is always improving. And so I'd like to think that we will continue to collect data maybe on those fringes where we didn't do as well in the past for whatever reason. And then that can in turn lead to maybe a little bit better calibrations of some of those models that you spoke of, and then, if you can sort of get a little bit, on those edges, on the margins where maybe there just wasn't either good data or any available, those will, kind of improve. So, I think it will be a combination of both. Once again, we can't put sensors everywhere. That work all the time, and so there's always going to be a need to transfer information to other locations, and I think this would be a growth area for monitoring, hopefully to then improve the science and improve those models.
Great, thank you. I have one more question for you, and maybe it's a little bit more on the personal side, but you spent a lot of time in Texas in the Houston area, and since at least 2015, it's just been flood event after flood event after snowfall event or whatever ends up happening in the area. Would you say you had any experiences over the last 5 years that really made you, look at hydrology in a different light where, I hadn't even thought about, that this could happen with this much rainfall? Can you think of any time that might have happened for you with what you've seen over the past 5 or 6 years?
Yeah, I mean, certainly in relations to flooding, when Hurricane Harvey, sort of came through the area, that was one that was, certainly unprecedented. And I will say this, that, I felt that the National Weather Service and their forecasting was, incredibly accurate and definitely, timely. That, I can remember the messaging they put out, ahead of time, that, they were using words that I hadn't seen before, catastrophic and other words that, they usually don't put those out, and they certainly don't put them out without thinking about it. And so, when you start seeing, predicted rainfall amounts over relatively large areas of 35 inches, et cetera, yeah, that's something that, you know, in my career, I just, you know, hadn't considered. And, you know, certainly tropical events will drop very intense rainfall in small pockets. You know, you can see very large numbers, you know, but usually they're in sort of, you know, localized. You know, looking at the area, and I don't remember the you know, all the math on it and the numbers, but, you know, 2,000 square miles, you know, or something had well over 20 inches of rain, you know, in a 2-day period. And, you know, as you start to go down, the recurrence intervals were greater than 500 year and so forth. So the spatial extent and, you know, how that interacted with a low gradient, you know, setting, you know, it just completely overwhelmed everything that we did. And, you know, we put gauges and think, you know, from the USGS side, if you've got a flood and you try to challenge us and say, you know, how are you going to measure this? You know, we take that as a challenge. It's like, I can measure anything. Well, this one, there were some places where, you know, we had to get very creative. You know, I was on a boat in East Texas and had to measure, you know, what usually is the Sabine River, you know, usually a couple hundred feet wide. It was 12 miles wide. So the magnitude of an event like that certainly, you know, got my attention, and you know, that does. You know, I'll say the other thing in coming to Houston. I'm originally from the Midwest. You know, I put the bullet, you know, water flows downhill. In the Houston area, I don't know that water really always flows downhill. That was something I had to learn, but it does flow down gradient. But sometimes I don't know which way the water flows downhill. So.
Well, thanks again, Jeff. I don't
We
see
did have
any
one
other
question, Mark.
Yeah, go ahead.
So, Jeff, we got a question for small areas, less than 10 acres. Would you think it would be better to leave out the infiltration factor?
Well, you know, it depends is sort of the real short answer. You know, generally you got something that small, it's going to react pretty quick no matter what. You know, does that mean, you know, if it's a parking lot, yeah, that's, you know, an incredibly fast, you know, response time. If you're talking about sort of a undeveloped, you know, field of some type, or, you know, still something that's, you know, bare earth or dirt or whatnot, you know, it still probably is going to respond pretty quick. But, you know, it would also depend on the scenario. If I'm looking at designing something, let's say, you know, maybe on a setting that small, I might, you know, and that would sort of just be a conservative, you know, I'm going to factor in a little bit of a factor of safety, and maybe over design just a hair for that. That's a pretty general comment, though, you know, ignoring a lot of other things that can happen. But small, you're absolutely right. When we start talking about very small size watersheds, there is some different responses than what we would normally see, and we don't have, you know, a ton of data on those sort of size watersheds, just because, you know, gauges and other things tend to be on bigger rivers or streams that affect, you know, you sort of want to capture as much as you can. And so the very small size watersheds, you know, there's information, a lot of research, but the responses is significantly different, and the timing especially is a difficult one to get a handle on.
Sounds good. I don't see anything else coming in, Jeff. That was very good. So unless you have anything else you would like to add, I think that can wrap us up.
No, I think that's it. You know, you know, I think I see at least, you know, one or two. You know, we're going to post this recording, you know, on the web for people to look at, and I've got my email up. If, you know, we can probably share the presentation in, you know, a number of different ways. If someone just wants to contact me directly, send me an email. I can email you a copy as well. but the recording is also going to be available if that's of more use. So, but otherwise, I think that's good, and we appreciate everyone's participation, and look forward to seeing people, I guess, next month.